Okay, one last video on number representations and binary. We'll get to those actual types of numbers in C very, very soon, but I just wanted to go over floating point numbers first before we go into, we finally get into the other stuff. So we'll actually get into C code very, very shortly, and hopefully that my PowerPoint slides are going to work. Okay, so anytime now. I don't know what's going on with this thing. Okay, so if it keeps on going, I may have to restart the video, but hopefully we won't. I may have to restart the video. Okay, so uh, it turns out, so when we're talking about linear numbers or linear representations of numbers, fairly easy to get your head around. Floating point numbers, on the other hand, are designed to be able to maximize the range of numbers that you can represent. So you cannot represent both ridiculously large and ridiculously small numbers sort of at the same time, or the granularity gets a little weird. What you end up having is, or really, you cannot represent extremely large numbers with extremely high precision down to like some ridiculously small number. It Floating point numbers and doubles, which is double precision floating point numbers, are called floating point numbers because there's no fixed decimal point. The idea is you would represent the number in a very similar way to scientific notation, as in you have a number with a positive or negative sign at the front, you have the actual number you're representing, like 3.158 or whatever the case is, and then some exponent value to represent how the magnitude of the number. So very much like you could say a kilometer is 1,000 meters, but you can also say 1 meter is 1.0 times 10 to the negative 3 kilometers. Right? The idea of a scientific notation is you do not have to show all the zeros and how all the decimal points. You can represent it by some exponent, the number you're representing, so the actual value, but not with the exponent part of it, and then the sign bit. Uh, this means though that it's kind of quirky in how you interpret it and very hard to actually read. It also means that there are some precision limits, even if you don't necessarily realize those precision limits are there. So, for at least for old systems, I'm not sure if this is still the case. I would have to run a size of for my Visual Studio, for example, and it's a good idea to never assume the size of any of these data types. A float oftentimes is 32 bits, and a double would be 64 bits. If you have a 64-bit system, it might float by maybe 64 bits, while the double is 128 bits. They're fairly large things, and they have a particular format to them. But depending on the compiler, depending on the operating system, they're going to be different sizes. But the bucket sizes are approximately 32 bits and then 64, double the size for a double. Now, um, yeah, and sometimes you can specify a float as a single, with meaning single precision, and then double for double precision. But most of the time, we just say float and double. Uh, Doubles and floats are there's a standard that is now being used regularly. But I mean, look at the date on this thing, IEEE, and it should be from 2008 when it was finally sort of nailed down more appropriately. 1985 was the version of this beforehand. They're pretty much used by all programming languages like C, C++, and Java, but it was a long, long time before we actually nailed it down to something very, very precise. Uh, and so, therefore, there are some little quirks when it comes to dealing with these numbers. Debugging can be difficult. Uh, so here's what the approach is. We'll have a sign bit. We'll have a bunch of exponent bits, 8 of them for a floating point number, and then we will also have 24 bits to 23 explicitly stored bits, but 24 bits in total. I have to look into that a little bit in a second. But we have the actual value that we're dealing with, a mantissa. We have the exponent bits, 2 to the power of negative 2 or 2 to the power of 24, whatever the case is. And we have a sign bit. So we have the actual number, we have an exponent, we have a sign bit, and all of these things working together will give you the actual. And so the actual number itself is, we have a sign bit, we have the mantissa, and then we have the exponent itself, and that will tell you what you can. So it will look something like this, and this would be, I'm assuming, exponent, this is the value itself, the mantissa. It would be very similar to saying something like this. So 1, 2, 5, 7, 9 times 10 to the 3. In fact, normally what we would do, let me clean this up a little tiny bit. Normally what we'd end up doing is say something like this. 1.2579, right? What is the speed of light, for example? So what E equals mc squared, what's the C? Right? It means something. Or you can have how much is a mole of, how many moles are there, how many atoms are in a mole of a chemical, right? If you talk about chemistry, this is used throughout. How much is a light year? How far is a light year? Right? It's a distance light travels in a year. That is a really big number, and we actually normally do a scientific notation for that. Something like this. Well, we're going to do a very similar thing here. So if I had, let's say, negative, and then we'll make it a -3 up here, right? We're going to do something very similar. We're going to have a sign bit. We're going to have the value, which is going to be this thing here. And then we're going to have an exponent bit, which is this thing here. Now, these are all 2 to the power of -3, or 2 to the power, 2 times, no, sorry, it'll be, instead of 10, it'll be a 2 to the power of -3, or 2 to the power of 17, or whatever the case is. So there's implicitly that this is 2 to the power of whatever this number here is. We have the value that we're actually doing here, and then we have a sign bit on the front. And with that, we actually can represent a really quite a large range. So the maximum value is this 18, whatever crazy number that is, right? For 64 bits of data at least. This is so 18 times 10 to the 18 as the largest value. The range for a double of 64 bits can go all the way down to this ridiculously large negative number, to this ridiculously small negative number, to this ridiculously small negative number, to this ridiculously large positive number, right? This is exponent 308. So 2 to the power of 308, 1.797 times 2 to the 2 to the 308. That is quite a large number. It gives you a very large range, but it does mean that you're going to get some rounding errors. And you can get some. The math is actually problematic. It turns out, much like, what's a third as a decimal point? It's 0.330. Wait, repeating, right? We get something very similar to that, and I'm not going to get into that detail either. 0.1 is the problem. Much like a third is a problem for decimal, 0.1 becomes a problem in binary. It gives you a repeating number, right? And so when you're doing these calculations, the numbers are not going to be dead on, or they're trying to be dead on, but sometimes things can go a little off. And so there's a lot of, if you're going to use floating point numbers, I would always urge caution whenever you're doing it, because it can be hard to debug afterwards. If you can deal with whole numbers, deal with whole numbers. If you need floating point numbers or doubles, go with doubles and floating point numbers. But we never actually go hardcore into how floating point numbers and doubles are actually stored in the system. I don't think anywhere in this degree. I don't think anywhere in any of the computer science degrees I've taught in other schools. I learned it briefly once when I was an undergrad, and even then it was sort of swept under the carpet, right? Unless you need it, you don't normally necessarily look it up. Versus everyone's expected to know two's complement because it gets used in wonderful, weird ways. All right, it also leads to other debugging issues. Hexadecimal, by the way, so I'm going to just shift gears on this one. I'm not going to be grilling you guys on doubles or floats. You should know that doubles and floats are going to be, you don't normally see if something is exactly equal to 0.0. You don't normally see if something is exactly equal to some number because of the level of precision that you have. It can often mean that the math won't work for you. You normally check to see if the value is greater than 0, and if it's not greater than 0, then you stop, for example. Right? You need to somehow do little tweaks to avoid the precision issues that you can sometimes introduce with floating point and doubles. But we've been talking about binary for a while. And I will also say, if we were using binary and only binary, I would hate everything about computer science. Well, you might hate it already, but there is a better way, right? We've been talking about binary numbers for a while, and you get these like, you know, let's represent a 32-bit binary number, and you write zeros and ones a whole bunch of times, and you accidentally forget a zero, and your number is completely wrong, and you get zero on your assignment, and you cry, right? It's they're not designed for humans to read. They're great for a computer. They're really terrible for a human. And we also know that it's a pain to go from decimal to binary because things you have to do all that math calculation. So if I have something like this is actually, I think, just uh, a compiled file or something like that. It's just bytecode. So this is just raw data. It's not human readable. It's not text or anything like that. If I have raw data and I just had zeros and ones everywhere, it would be impossible for me to read. It would just be this wall of zeros and ones. I cannot read a movie as zeros and ones. It's just too much for any human to understand or be able to interpret. What we want is a convenient way to let us look at what the computer is actually seeing without actually looking exactly what the computer is seeing. If I'm not able to look directly at the zeros and ones because it's too much for the human eye to be able to process, I need something better. And what do? Well, let's chunk things. Now, we can't go from decimal to binary easily because one's base 10, one's base 2. That leads to mathematical issues. You have to do that calculation all the time. What if we did a different approach? What if we take another power of 2 that's going to look closer to decimal that we can actually use? And that's where hexadecimal comes in. It's actually a misnomer. Hexadecimal suggests that it is um, six tens or something like that, like power of 60 or something like that, right? It is actually 6 hex and 10 decimal, meaning 16. This is base 16 numbers that we're going to be talking about next. So instead of doing 0 and 1 only, what if we take 4 of those bits, those zeros and ones, take any 4 of them, bundle them up, much like, here we go, let's pretend I'm a prisoner somewhere. All right, 1, 2, 3, 4, 5, and 1, 2, 3. How many items do I have there? I have 13. Why? Because I can quickly bundle up the 5, 10, and then add the other 3. I bundle numbers. This is a natural human response. Well, why don't we bundle 4 zeros and ones together, 4 bits together? That goes up from 0 to 15, so it gives me a maximum range of 16, so it's a base 16. Instead of base 2 or base 10, it's base 16. And since it's a power of 2, it's actually a power of 2, which is a power of 2. Because we really love powers of 2, I told you, right? Because it's a power of 2, there's a one-to-one correspondence always between binary and hexadecimal. I can always take any 4 bits of binary, convert it to the same hexadecimal number. So I'll be beating that to death very shortly, but just that's the premise that we're working with. I want something that I can read as a human, but under the hood actually is representing the binary. So I can see the binary in a more human readable format. It's still binary, but I have a human readable way of looking at it. So binary and hexadecimal. So binary and hexadecimal, they one-to-one map between the two of them. Binary gets invented, with the first computer, and pretty much the moment they do that, they go, "Oh hell no," and they make assembly, right? And while they make assembly, they go, "Oh hell no, I don't want to look at, I don't want to look even at assembly. I'm going to make compiled languages, and I'm not even going to look at binary numbers. I'm going to bundle up my binary numbers into a more meaningful, easier to read format, so people can read the code, read what's going on. Because if I have 32 ones and zeros, there's no way in heck I'm finding out what that means." Right? So what I want to do is just take groups of 4, convert that to something else so I can actually read the number. This is much like you do not read individual characters and make out a word, you read the word as a whole, right? We chunk things. So compiled languages are invented in the 1950s. Assemblies are invented in the 1940s. The moment we have binary, we get rid of it for humans and we convert it to hexadecimal because we know it's impossible to read. We know it's too hard. So we're not ever going, I might ask you for a couple bits of binary, but we're going to be dealing with hexadecimal for the vast, vast majority of things. We will convert to a binary number and then immediately convert to hexadecimal. Hexadecimal always just represents the binary number. There is a one-to-one mapping between the two of them. You don't have to worry about where you chunk things or, oh, how many bits do we have? It always works. So, you also can't, by the way, put directly put in binary. You can directly put in hexadecimal. That's not a problem. But most systems will not let you put in binary straight. It's just, and it's way too hard to get your head around. So here's the interesting thing. So why don't we do, if we use decimal, what would we get? So what is 100 in decimal? Well, here is we would need to take. I'm not going to take that breather right now. I'm going to just do this instead. So what is 100 in decimal? I would need to, it would be a 64 and then probably 32 and a couple other things in there. I also guarantee that 1000 in binary is not the same. So let's do this. 100 in decimal is going to be equal to 64, 32, 16. Just to show you this again, 4, 2, 1. Right. I know I have 64 in there. I'm going to take away that 64 from 100. So what does that give me? That is going to be 36, right? Should be. Yep, 36. All right, so I have another 1 here. And that's going to be equal to 4. Okay, so 0, 0, 1, 0, 0. That's 100. And one other digit. Okay, just all I did was add a 0 at the end here. You'll notice the binary number that we're going to get out of this thing is going to be radically different than what we had before. So 512, 256, 128, 64, 32, 16, 8, 4, 2, 1. This is why people have memorized binary numbers, because when you do this enough times, it just sticks in your head. Okay, we're going to have a 512 for sure. We're going to have a 256 for sure. We're probably going to have a 128 in there somewhere, but I don't know for sure. I should probably break out my calculator and just look at those, right? But already it's a different number. It's not 1100. It's not going to be 1100. So if I had 512, all right, but I'll let you break out your calculator, or maybe I'll come back to the video and fill in this in later. It's going to end up being that's 768, and that's 8. Okay, almost 900. Then I can add another 4, so that's going to be there's going to be 1 there, and there's probably going to be a couple other things in here. It's almost going to be the full. Actually, it's almost going to be the full thing, other than 24, because it's 1024 is the next power of 2. So if I subtract 24, I'm going to essentially, most of these, there's going to be a 1 here too, and there's going to be like a couple of, there's going to be a 0 here, and maybe there's a 1 here. But it's not the same number at all. I'm just approximating because I don't want to actually do the math, because I'm not that great at basic arithmetic. But the point is that the binary numbers are radically different. I just put another 0 in there, and I have a completely different binary number. I would have to translate every single number every single time. Versus, I add a couple other bits, I want the number to almost be the same, right? I want to approximate what binary looks like. So, let's do powers of 2. Hexadecimal gives me another power of 2. It's 2 to the power of 2 to the power of 2. 16 is equal to 2 to the power of 4, which is equal to 2 to the power of 2 to the power of 2. Right? And so in the case of decimal, so when we actually do this, we want it to make sure that it's consistent. If, by the way, if we take a number in binary, here's a binary number, that's 3. We add another, we change things around. We put a 1 in front of it, or we put just another 1 in here. The things are not consistent at all between the two number systems. So what we really want is a direct matching between decimal, from between binary, and something we can read. So I should have gotten rid of this thing. So let's count 15. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. What the? What? Yes, we need some way of representing up to 16 numbers. And computer scientists are efficiently lazy. Or programmers in general are efficiently lazy. So we want something we can type on a damn keyboard and not have to worry about it. Right? We don't want to have some special Greek character and stuff like that. That's the first thing we get rid of every time we have a chance. Right? We want something that we can type. And the easiest thing to type is things you're not going to be using afterwards. The letters of the alphabet work just fine, thank you very much. And so hexadecimal counts to 15. And after we get to 9, we need another set of characters to represent 10 up to 15. We use the letters of the alphabet. So here we go. 0 to F. F would be all ones. A is, or what is effectively the equivalent to the value 10, is 1010. 1011 is B. 1100 is C, and so forth and so on. Notice that it's a consistent 4 chunks. Any 4 chunks of any 4 bits that you have that look 1101 is a D. You don't have to worry about where it's shifted or anything like that. Just grab bundles of 4 bits and convert it to hex, and it will work every single time. It does not work like that for decimal. I can't just take a chunk of 4 bits, convert the decimal number over, and take another chunk of 4 bits and convert the decimal number over. It doesn't work that way. So I need chunks. I can just take groups of 4 and convert it to a hexadecimal number. So here's what we're doing. So here is AABB881. Okay, A is consistently 1010. So I can just do that again. The next thing, B, 1011, 1011. I just blindly put those down. 8 is always 1000. 1 is 0001, right? It doesn't matter how many of these things you get, you put another 2, you put another, let's say a 2 afterwards. I just add another 4 bits. It doesn't matter how big the binary number is, I get the same result. It's consistently chunk by chunk, 4 bits of binary number is equal to 1 hexadecimal number. I don't have to worry about spacing or where I chunk it. It always works out the same way. Okay, that's what I want. I want something that I can look at chunks of binary numbers at a time and interpret them. So what I want to be able to do is, if I see F, 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 what is that? That is, and we'll talk about this in a second. So F, 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 4 hexadecimal numbers. Each F is 1, 1, 1, 1. They're all ones. So this is all ones. Notice when we did 2's complement, what did all ones mean? When we did 2's complement, that was always -1. That is -1 as a, 4 times 4, 16-bit binary number. It represents -1. And you get used to seeing this pattern over and over and over again. You'll get used to it when you get more experience with it. And so oftentimes you'll see 255 as well, which is 2 hexadecimal numbers in a row. 55 is an 8-bit binary number. Why? Because I know each one of these bits, or each one of these digits, is 4 bits. That's 4 bits. That's 4 bits. 2 of them together makes 8 bits. This is 1, 2, 3, 4. 4 times 4, 16-bit number, right? This is, how many of these are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4, 32. 32-bit number, right? There's a really nice correspondence between binary and hexadecimal numbers, and allows me to really parse it quite quickly. It also allows me to take one chunk of numbers, take another chunk of numbers. So, for example, makes the math easier. If I add this number and this number together, I get this number. Why? Because this number is not going to interact with this number at all. The digits are completely separate from each other. So I could take F0 plus 0F, and it will give me FF, right? It's the same idea. As long as I have a 0 in one of those positions, it's not going to affect the other numbers, and I don't have to worry about, rolling over or anything like that. There are little shortcuts I can do. Uh, by the way, you'll see this. When I do this, I keep on, for myself, I consistent I try to consistently use 0x to represent a hexadecimal number. Why? Because when I get to Visual Studio, that's what it's using to represent a hexadecimal number. That's the only reason I use that format, because hexadecimal numbers are represented using 0x in Visual Studio. We could have also put a base 16 thing right here, or just H for hex. Both of those also work. But the 0x is just because you're going to see it again and again in Visual Studio. So hexadecimal numbers, we sometimes, if you see 1, 2, 3, 4, you don't know if it's base 10, base 2. Well, actually, you know it's not base 2, but it may not. It might be base 8. It might be base 16. You don't know, and so having some kind of indicator that it's hexadecimal or octal, which is base 8, or decimal, is critically important. I like to point out this is actually not my IP address, just in case you're wanting to hack me, because I know students that have tried that sort of thing. Where the heck are these IP addresses coming from? Why is there a dot in between? The dot is in between because they're not showing a hexadecimal number technically. This is 221 as a decimal number, but under the hood it's actually a binary number. Under the hood, this is whatever the let's take 255. These are chunks of 8 bits. Each one of these are 8 bits. This is a really big 8, 16, 24, 32, right? So this is 32-bit. This is a 32-bit number to represent your IP address. And each of those dots is representing 8 bits or 2 hexadecimal numbers in chunks. When we talk about bit flags later on, we'll see this in action. We'll see why this is important. Why but it's a binary number. It's not a decimal number like it looks like. It's not 192. It's some binary number that we're using. And converting it to hex helps you understand what's going on with this, why the number looks the way it does, or see how it consistently works. When we do bit flags, we'll also see why we need to know binary and hex. So, it turns out there's a bunch of weird places where this gets used. First of all, there is a famous example of the Patriot missile going awry during the Gulf War, the first Gulf War, George H.W. Bush. Now, this is before you were born, so please hear me out on this one. It turns out, during the Gulf War, Saddam Hussein had Scud missiles. He had these missiles that he could shoot off into, at U.S. bunkers, for example, or at civilian targets. The Patriot missiles were missiles set up that would shoot down incoming missiles. They're missiles to shoot missiles, essentially. And you'd plug them in, they'd be constantly surveying the area, and when a missile was coming in, it would shoot down the missile. One of the Patriot missiles did not work correctly and missed the target. The Scud missile ended up hitting a U.S. bunker, and it killed I think it's over 60 U.S. Servicemen. The reason it missed the target was not because the system, made an oopsie or anything like that. Well, there was an oopsie, but not the oopsie you would expect. It missed the target because when you plug in one of these things, and it's plugged into an some kind of electrical system, when you plug in one of these things and the computer is running on it, at a certain point in time, the precision or the number that you're storing is too big and it overflows because it has to keep down to the millisecond for the timing for the Scud missiles. At some point in time, you run out of precision for this, and you get an overflow. The number that you're storing for the time, how long it's been on for, is too much, and it overflows. And your timing your missile is off, and people die. The actual solution to this problem is honest to God, I'm not making this up, is to unplug it and plug it back in again about once a week. That was the actual solution to make sure that it doesn't happen again. Is turn it off and on again, because you reset the counter and you don't overflow the counter in the end. When we're talking about IP addresses, we use bit masks. Those are going to be used again and again and again, especially if you're doing any kind of network stuff, all based on binary, right? And you'll be looking at hex as well. Why is your home address, network address working the way it does? How do you make sure you reroute a packet from one place to another? All based on binary. They're not using decimal, they're using binary. And when they had a Belgian vote for, I think, I don't even remember I think it was a local election in the end, but they were voting in Belgium, this small town in Belgium, and this radical, more extreme candidate got way more votes than they expected, or an order of thousands more votes than they expected. What's even more strange is that I think they got more votes than there were people in the town that were voting. When they actually dug into it further, they found out it was off by some one power of two. It was something like 2048 that was off, or some number like that. So which is another power of two. It turns out that if you screw up one bit in a number and you don't have a redundancy in your system, the number of votes, the vote tally that they had, the bit flipped from a 0 to a 1 by accident or whatever the case caused this thing. They're thinking cosmic rays. Uh, if you flip that one bit from a 0 to a 1, suddenly radical extreme people that do not get that many votes suddenly get thousands more votes than they should have, just because of a single 1 or a 0. That's how we debug stuff. So when we're debugging our code, this is actually what we have to look at. Why is the number wrong? Why is it when when I subtract a number from this, I suddenly get this massively? I've literally written code where I'm counting down from 400 down to 0, and I'm supposed to stop. And I count down from 400, and I have an infinite loop, and it just keeps going around and around and around, and it never stops. And the problem is, I have an unsigned value, an unsigned integer. So I have a number that's only considered positive. And when I get down to 0 and I subtract 1, what happens? It becomes a huge positive number again. It loops around instead of becoming -1. This is the reason you need to understand this, because otherwise you can't debug your code. Okay, so next time around, we're going to be looking at a much higher level stuff. This is really low level stuff when it comes to just looking at binary. We need to look at it sometimes, but I like looking at a higher level stuff most of the time. Hexadecimal allows you to look at a higher level than just pure binary. But you still know exactly what the CPU is doing, which is really the nicety of it. So C++ and C rely on binary more than most other high level languages. You'll actually need to look at what your memory looks like when you're debugging your code, and hexadecimal is the way to figure out what the correspondence, what the number actually is. You can figure out what the binary number is, and then figure out what the decimal number is and what's going on with your code. The only way you can debug your code is to be able to figure out what the computer is doing, line by line, step by step. And the only way to do that is to know how it's doing it under the hood, and that's what we were doing now. Next time around, we're going to actually finally start with C++, and it's going to be we'll finally get to code some things in C++, or in C at least. So with that being said, I'll take my leave of you guys, and thanks for listening.